Hello, my name is Gina Galindo, and I'm here to share with you this research using OR to search for a missing person under dynamic disaster settings. Thank you for being here attending this Informs webinar. This research is a result of the dissertation of my former graduate student, Dr. Jose Daniel Betancourt Reyes, and other co-authors are Dr. Ruben G. and Dr. Alfredo Moreno from Universidad del Norte. So this is a brief outline of what we're going to see today. Let's start with the problem setting and motivation. So let's say that we have this region where we have an ongoing dynamic event, such as a wildfire. And we know there is a missing person here who is injured and not able to move away from the disaster. So we need to go and search and rescue this person. The problem is that we don't know for sure where to find this person. We do know there are some locations where it is more likely to find this person. We also know that the disaster is not static, but evolving, okay? So we know that this disaster is moving, and also we have this information about where we may find this missing person who is immobile. So now that we have outlined the problem setting and the motivation, let's address the research question. So basically, we have a missing immobile person in a region where we have a dynamic ongoing disaster event. So we want to perform the search, prioritizing these two objectives. Okay, we want to search first in the locations which are more prone to be affected first by the dynamic threat. But at the same time, we want also to prioritize the search in those locations where it is more likely to find the person. So how to do that? So let's divide the region into a set of cells, and then these cells are going to be represented as nodes in a network. So we have this missing person, we don't know where. We have this dynamic event. What we want to do is to monitor the event in order to forecast how that event is going to evolve and try to see which nodes are going to be affected first. Also, we want to use information about where it is more likely to find the person, okay? And we want to combine these two things into a mathematical model to plan for the search. In that search, we want to explore, of course, here where it is more likely to find the person, but also we don't want to forget about these cells which are more likely to be reached by the disaster sooner. Because if the person is here, then we should hurry up in order to look into these cells so we can find the person under good conditions. So now let's talk about the methodology. We have a multi-objective mixed internal linear programming model where we have two objectives. The first objective relates to risk. We want to cover first those cells or those nodes which are more in risk to be reached by the disaster. So we have a risk coefficient for each cell, and we multiply that coefficient to the time of the number of scans that we have done to that cell. So in this way, we want to look first into the nodes that are more likely to be reached by the disaster sooner. On the other hand, we have this second objective where we consider the probability of successfully finding the person. So here we consider the reliability of the agent because we assume that the agents are not perfect. Okay, so there is a reliability of agent. And also we consider the probability that the person is actually in the cell where the agent is scanning. So in this objective, we want to look first into the cells where it is more likely to find the person. So we have a mathematical model with those two objectives. And an interesting thing is that we consider that the search agents are not perfect and they may give us some false negatives. Okay, so maybe the agent didn't find the person when scanning a cell, given that the person is actually there. That may happen. So we want to update, using a Bayesian approach, the conditional probability that the person is in a given cell, given that we scanned that cell and we didn't find the person. Okay, so this is this conditional probability, which is nonlinear, and that leaves us with a mixed integer nonlinear programming model with the two objectives that we just saw. And we have some constraints about routing, about scheduling, which are linear, but then we have this nonlinear constraint, which relates to that conditional probability. So what we did was we used a piecewise linear approximation for that constraint, and at the end, we were able to obtain a mixed integer linear programming model for our problem. We used three different approaches to solve the model: an adaptive epsilon constraint, a lexicographic method, and a multi-objective, multi-agent, and colony approach. So basically, we also have a moving horizon approach because we want to do all of these stages: monitoring, forecasting, planning the search, and exploring during different or during multiple time windows until we find the missing person or the region is completely burnt out. So if during the first time window we don't find the person, then we're gonna continue our search with the same stages until, as I said, we found the person or the region is exhausted by the fire. And at each time window, what we're going to have is a schedule for each agent to perform the search. So now let's see some of the results that we have so far. We have used the cellular automata process to simulate the wildfire evolution. We also have some information about agents. We have heterogeneous agents with different speeds, reliabilities, exploration times. And then this is some results for small instances of the problem. Here we have the first objective about the risk. The second objective is here, which relates to successfully finding the person. And then here we have the Pareto front from the three different solution approaches. As you can see, the lexicographic method was able to find the extreme points of the Pareto front, and the N colony and the E constraint was able to find extreme points, and the N colony and lexicographic were able to find the same points of the Pareto front. This is for small instances. Then we moved forward for larger instances. In those cases, the E-constraint method, in terms of computational time, started to struggle. Lexicographic approach was, at the beginning, was doing okay, but then with larger instances, the computational time also became too large. And here in the first column, what we have is the Ant colony approach, which had very decent computational times, and also the gap to the optimal solution so far is also very satisfactory. So as we can see, the heuristic outperformed the other two methods. This is a simulation of the whole mission under different configurations. Here we have the wildfire, and then here we have the probability of a person being in these cells. And what we wanted to assess here was the effectiveness rate, which is the percentage of the time in which the missing person was actually found. And here we had a 60-70% effectiveness rate, which is something that we definitely want to improve. So now I'm just going through some conclusions. So our model is a novel methodology for searching an immobile entity under a dynamic setting. We use a moving horizon multi-objective optimization model with different solution approaches. And we definitely want to consider different features such as moving on multiple targets, other types of disasters, and also we want to improve that effectiveness rates. Potential applications include other types of disasters. And that's it. Thank you so much.